All right, hello one more time. We are going to discuss section 10.6, which involves thermochemistry. So we've been talking about energy, we talked about calories and joules and specific heat capacity, and now we're going to talk about what's called enthalpy. Well, the symbol for enthalpy is a capital H, okay, and it's the amount of energy that's either produced or absorbed in a reaction. Well, delta H, remember delta means change, so final energy minus initial energy, and sub P is the heat, and this is for a reaction that's under constant pressure. And so we're trying to keep some things the same while we change the amount of heat and look at temperature. So enthalpy change is the same as saying the heat for reaction, so we can interchange those terms. And enthalpy is also a state function. It doesn't depend on how we get there. All we're looking at are the initial and final conditions. So let's look at an example. Let's get a pen here. Okay, so we have 1 mole of methane, which is CH4. It's burned at a constant pressure, and 890 kilojoules of energy is released as heat. So for every 1 mole of CH4, we're going to get 890 kilojoules. Now, this says that it is released. Because it's released, it's leaving the system, we're going to make it negative. That also makes this an exothermic reaction, okay, because heat's being given off. Okay, they want us to calculate the delta H, the change in enthalpy, for a process in which a 5.8 gram sample of methane is burned at constant pressure. Okay, so here's what we need to do. We know that for 1 mole, this is the amount of heat that is released. But we only have 5.8 grams. So this relationship is going to become our conversion factor, and we're going to use that to go from grams to kilojoules. Okay, so let's start with the grams. Start with what we're given in the problem. So 5.8 grams of CH4. Now, in order to go from grams to moles, we need molar mass. So for every 1 mole of CH4, well, carbon is 12.01. Each hydrogen is about 1, so we're going to say 4. So that's going to give us about 16 grams. Okay, and we could stop here and calculate and then do our next one, but we're just going to go all one step. So we've canceled out our grams, and now we're at moles, and now we can use our mole to kilojoules conversion factor. So for every 1 mole of CH4, and I want it on the bottom so we'll cancel, there are negative 890 kilojoules released. Okay, so take your calculator. We're going to multiply anything on top, divide anything on the bottom. So we're going to take our 5.8 divided by 16 times negative 890. And we get negative 322.625. Okay, and that's kilojoules. And now we need to determine significant figures. So if we look up here, now this was a conversion factor, so these don't technically count. We're looking at what we started with in the problem, and that would be 5.8, so we have 2. So we're going to round here. This 2 will not influence this one, so we get negative 320 kilojoules of heat released for every 5.8 grams of methane. Okay, well, a lot of ways that we can calculate the enthalpy has to do with what's called calorimetry. A calorimeter is a device used to determine the heat or the enthalpy associated with a chemical reaction. And we can find delta H, which is our change in enthalpy, by knowing the temperature change of our substance and the heat capacity of the calorimeter. How good is the calorimeter trapping heat? So we've got a very simple setup here, which involves 2 styrofoam cups, a way to stir the solution, and a temperature, so we can measure or a thermometer, so we can measure temperature change. We've also got one over here that is much more fancy. So if you do a calorimetry experiment in college, you would probably use something like this. This is actually called a bomb calorimeter. Kind of looks like a bomb. Everything's contained. Okay, we've got oxygen supply into the substance because you need oxygen to burn. It's totally insulated. We've got water surrounding it so we can pick up the heat given off by the substance. You've got your substance. You've got an ignition coil to light it and burn it. And then up here, this is where you would try to light it because everything is contained. You can't really get in there. And then we've also got a stirrer. So although they are the same in principle, this one is much fancier. Fortunately, we won't be using one of those fancy ones. Okay, let's look at another example. Okay, so the reaction that occurs in heat packs used to treat sports injuries is iron plus oxygen goes to iron 3 oxide. And the heat given off in this reaction is negative 1,652 kilojoules. We want to know how much heat is released, so we're looking for joules, when we have 1 gram of iron and excess O2. So this is in excess, we're not going to worry about it. Okay, so what this means is that the first thing we have to do is balance our equation. Well, if I have 2 oxygens here and 3 here, I want a number that's going to make them the same. So I want 6. So if I put a 2 in front, that makes 6 oxygens there. A 3 here gives me 6 oxygens for my reactant. And then the last thing I need to do is my iron. 2 times 2 irons gives me 4. Okay, so I'm going to start with what I'm given in the problem, which is my 1 gram of iron. Now, in order to use this, because for every 4 moles of iron, this much heat is given off. For every 3 moles of oxygen, this much heat is given off. And for every 2 moles of iron 2 oxide, this much heat is given off. So in order to use this conversion factor, I need to get to moles. So I'm going to use the molar mass of iron, which is 55.85 grams per mole. So my grams go on the bottom. Now I can use the relationship between my 4 moles of iron and the amount of heat given off in the reaction. So for every 4 moles of iron that I use, I know that it's going to give off negative 1,652 kilojoules. I could also base this on oxygen or the product. It's kind of like a mole ratio. Everything's related through those coefficients. Okay, my moles are going to cancel. My grams are going to cancel. And now I need to calculate. So I'm going to take my 1 divided by 55.85 because it's on the bottom. And then I'm going to multiply by my negative 1,652 kilojoules. And that gives me negative 29.579 kilojoules. Okay, let's look at significant figures. Since this is what I was given in the problem, and there are 3 significant figures, that's what I want my answer. So that rounds here. The 7 is going to round the 5 to a 6. So negative 29.6 kilojoules are given off when I have 1 gram of iron. So because this delta H value is negative, that implies that this reaction is exothermic because heat is being lost from the system. Alright, so here are some practice problems for you, and we will discuss this and go over some more examples in class. Have a good day.